Okay, Algebra 1, Section 8.2, Graphing Parabolas, which we started doing in the last section. But this time they're going to be of the form fx equals ax squared plus c. So this is the new thing. Just put your name, date, period. So let's see, today's goal is to identify characteristics of quadratic functions and graph using fx equals ax squared plus c. So that's today's goal. Okay, so as sort of an example and also review, so this will be example 1. So a little bit of review. We're going to go ahead and graph fx equals x squared. Now, fx equals x squared is a very special case scenario where the a value is 1 and the c value is 0. We call this the parent function. So f of x equals x squared is the parent function, okay? So it's sort of like the main one that all the others are based off of. So what we could do is we could make a function table and where we just plug some values in. -2, -1, 0, 1, 2. You can pick whatever x's you want. These are some good ones. And we'll plug them in here, -2. The negative gets squared, so it's -2 times -2 is positive 4. -1 times -1 is positive 1. 0 times 0 is 0. 1 times 1 is 1. 2 times 2 is 4. You kind of get this with parabolas. There's a left side and right side that kind of match up. So a lot of times we get the same y values on both sides of the middle of the graph. So now I'm going to leave a little bit of room here because in a second we're going to graph g of x equals x squared plus 6. But we're going to put them on the same graph. So if you have graph paper doing all these notes, I'm just doing them all on graph paper. It'll probably make it a little quicker, easier, and nicer. But I'm going to just kind of fake it and do the best I can. Now I'm going to make these my axes. These are called the axes. They should have arrows on the ends. So this is the x and y axes. I'm going to make them a little darker because I'm going to draw my own graph paper essentially. So I'm going to try and draw straight lines that are kind of equally spaced. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm just doing 10 in each direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. So I'm going to graph these on here. So negative. Now there's a pattern And I encourage you, if you feel comfortable with it, start taking advantage of it, and we could maybe not have to do the function tables as much. So whenever you plug something into a parabola, if you plug 0 and it gets squared, it's 0. If you go over 1, it's going to be up 1 squared, which is 1. If you go over 2 from the middle, you're going to go up 2 squared is 4. Over 2, up 4. And if you look at these points, negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4, it's all the same dots. In fact, I could go over real quick again. Over 3 up, what do you think it's going to be? What's 3 squared? 9. 4, 5, 6, 7, 8, 9. Over 3, up 9. Left to right, you go up. The number of squares squared. So you draw a nice curve here. It should not be a V. Goes through the dots. We should put arrows on the ends, which indicates it keeps going forever, which it does. It means we don't have to graph it forever to show that it goes forever. And this graph is fx equals x squared. The origin right here, sorry, not the origin, the vertex, which is at 0, 0. It's kind of an important point in the graph where it turns around. Axis symmetry is x equals 0. So that's called the parent function. So let's do this one. And we can make a function table. I'll show you how we can maybe get away without it. Let's do it in a different color. Let's do the graph in a different color too, just to make it easier to identify which one's which. So use pencil or some other color. So here, if you do negative squared, it's 4. And you can start writing this. 4 plus 6 is 10, right? The negative gets squared, so it becomes positive. Negative 1 squared is 1, plus 6 is 7. 0 squared is 0, plus 6 is 6. 1 squared is 1, plus 6 is 7. 2 squared is 4, plus 6 is 10. We get these matching up. Now, let me show you the trick. If we didn't want to do this, these parabolas, they all kind of have the same shape, but it gets changed, stretched, or shifted, or whatever. All these, what's happening is every y value that you would have got from the parent function, the normal shape, you're going to add 6 to every y value. So instead of starting at 0, 0, we're going to start 6 above it. 1, 2, 3, 4, 5, 6. That's our vertex now. Our vertex is at 0, 6. And then it has the same shape. You go over 1, up 1 squared on both sides. Over 2, up 2 squareds on both sides. And now if we look at our function table, that should give us the same dot. So negative 2, 10 is all the way up here, right? Negative 1, 7's right here. 0, 6 is here. 1, 7's here. 2, 10 is here. So you get that. This is gx equals x squared plus 6. Now, if you look at this, some of the graphs that we were looking at last time, they got skinnier or they got stretched or kind of squished. This shape looks exactly the same as this shape. No stretching. It's just been moved up 6 points. Every dot here got moved up 6 points, which makes sense. You're going to add 6 to every y value you would have got before. So all the y values are going to be 6 higher than they were before. And the effect for any kind of shape that you graph in the future, if you add 6 to the function, it's just going to move it all up 6. Now, so it's the same shape and size as the original graph, right? But it's been shifted up 6 units. Okay. Now, on your assignments and things, it's going to say to compare the graph to the parent function. Okay. That's what they'll tell you do. And that's kind of what I was doing here, but we can do it a little more technical, use the more technical language. So g equals x squared plus 6 is when you move something up or down, that's up or down is vertical. That's a fancy word for up or down. Vertical translation. Instead of say shift or move, we say translation. That's a fancy word for moving the graph up and down or sliding it up and down. Okay. And then we'd say 6 units. That's how much, and up tells you the direction. So we say vertical if it's up or down. We're going to look at some later that move left to right. That'd be horizontal. So vertical is up, down. Translation is a fancy word for shift or slide or move. Okay. So that's what we're going to be doing. Now, here's the thing. This C value, as I was saying, it's just, if you add 6, it's going to move everything up 6. If you were to subtract 6, it would move everything down 6. Okay. So the sort of our notes could be, if C is greater than 0, it's a vertical translation up. If C is less than 0, it's a vertical translation down. Okay. All right, let's do another one. So this one, example 2. We're going to do the same kind of thing. The directions are going to say graph f of x equals x squared on each of the following graphs. Then graph the second function gx equals, and this time it's going to be negative x squared minus 7 on the same graph in a different color. Okay. So we're going to graph the parent function, just like we did before. I'm going to graph this new one. Okay. So I'm going to go and draw my graph over here, or use graph paper. You can just use graph paper for the whole homework assignment, for any work you show, and your whole notes if you want. But I'm going to fake it and draw my own graph paper real quick. So I'm going to do 10 in each direction. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. You should want to do graph paper after this experience, right? It's not fun drawing these. And I do a pretty good job. I think mine look pretty good. I can draw a pretty straight line. Yours might be a little rougher. Okay, so let's say either we could use the function table above, or even just start to use our memory. Like, oh, the parent function starts at 0, 0, has a vertex of 0, 0, right? And the general shape is, however much you go over, you go up that much squared. You go over 1, you go up 1 squared, which is 1. If you go over 2, not from the last point, but back from the middle, you go over 2, you go up 2 squared, which is 4. 1, 2, 3, 4. And we could even go over 3 up 9. 4, 5, 6, 7, 8, 9. On both sides, because it's symmetric. So I can do that Seems like a simple pattern to remember if I've done it enough. So that's that graph. This is the f of x equals x squared graph. That's a parent function. Now this one right here, let's make a table. This one's going to be a little more complicated. So I'm going to probably show a little more work here. So now this one's interesting. It has this negative in front. What does that do to the graph? Okay, now here, when you plug in, so you have a negative and then you plug -2 in, squared minus 7. Well, the -2 gets squared, it's +4, but there's still a negative in front of it. That didn't get squared. It's like a -1 times it. Order of operations, PEMDAS, is to do parentheses, exponents, then multiplication. So we actually get -11. So be careful. So -1 squared minus 7. -1 minus 7 equals -8. The other thing that some people might think happens is like, oh, a negative times a negative, negative becomes positive. Well, that's multiplication, and you're doing it too soon because you got to do your exponents first. So you can't do minus becomes plus here because of the exponent. -0 squared minus 7 equals 0 minus 7 equals -7. -1 squared. So this negative isn't getting squared. That's why you need to write these parentheses. Just the 1 is getting squared. So it's -1 minus 7 equals -8. Okay, so we could graph these. Now, I'm going to tell you, I could do this without that function table because the -7 is going to move everything down 7, okay? But a negative in front of it flips the graph upside down, okay? So what I know is that 0, 0 is going to get moved down 7. 1, 2, 3, 4, 5, 6, 7. This is the vertex now at 0, -7. Okay, and if you look at this graph right there, 0, -7. Okay, the effect on this other graph is the parent function. Remember, usually I'm like, okay, well, if there's a number in front, you're going to multiply all the ups by that amount, or or subtract 7. But this negative has to happen first. It's going to flip it from +1 down to -1. So instead of over 1 up 1, it's going to be over 1 down 1, and then down another 7. Just going to put it at -8 on both sides. You look at this, -1, -8, 1, -8. Okay, instead of over 2 up 4, it's going to be over 2 down 4 because of the negative, and then down another 7 because of the -7. So that's your graph. So that was a little more complicated. I had a couple changes, but what happened here is that the graph got flipped because the a value equaled -1. Okay, and then it got shifted down 7. So there's 2 changes that happen here. So we're going to put that in words. Graph of g of x is a 1 reflection over the x-axis. Reflection means like a mirror image, to flip something. Okay, so I said flip, but a fancy word is reflect. Cross the x-axis right here, so that means you're flipping across the x. The other change was that it's also a vertical translation. Translation is a fancy word for moving it up and down, left and right. Translation down 7. So this is the comparison part of your answer. Okay. All right. Let's do another example. This one's going to be a little different. bit similar. Example 3. So in this example, we're going to find the zeros of the function. And then we're going to graph it. Now, finding the zeros of the function, that should sound familiar. That's something we were doing before we started graphing these parabolas. Probably means we're going to factor. Okay, remember how to factor? Okay, so part A of example 3. We're going to do y equals x squared minus 1. Now, the way you find zeros is you make the function equal to 0. That's what a 0 is. It's what do you plug in for x to make the function go to 0, make the y value to 0. So we get this, then we do some factoring. X times x, 1 times 1, right? And get x, get 1. And then you might remember this pattern here. This is sum of the difference of squares. If you don't, you can say, all right, 1x, 1x. They got to add up to 0x because there's no x terms in the middle. So one's got to be positive, one's got to be negative. So it's going to be plus 1 and minus 1. Now from there, we set these equal to 0. That's called the zero product property. We set each of these equal 0 on their own because if it equals 0 on its own, it should be a solution. And then we solve them. So these are your zeros. And we didn't even do anything new. This is all old stuff. Now, if we're to graph it, we can actually use these guys to help us graph this parabola, because this is a parabola. Right? I mean, you guys should get to a point where you can predict what this graph's going to look like without even doing it. That's the parent function, y equals x squared, and then the minus 1 is going to move it all down 1. So it's going to look just like the regular parent function shifted down 1. So what we could do is we could graph these zeros. Zeros are also x-intercepts. It's where the y equals 0, which is on the x-axis. So this is a 0 at -1, and this is a 0 at +1. And our graph of our parabola should go through these points. Now, we can make a table. -2, -1, 0, 1, 2. So if we plug -2 in, it gets squared, it's 4, and then you subtract 1, you get 3. -1, the negative gets squared because it's going to be inside the parentheses. 1 minus 1 is 0. Hey, -1 actually does give you a 0. Plug 0 in, get 0 minus 1 is -1. Plug 1 in, 1 squared is 1, minus 1 is 0. Hey, that's the other 0. 2 squared is 4, minus 1 is 3. So then we could graph it. -2, up 3, -1, 0, 0, -1, 1, 1, 2, 3. And if we connect the dots, it looks like a pretty normal parabola shape. Y is not stretched or anything, but it's been moved down 1, right? Everything's down 1. Now, I think I could have graphed this without making the table. I could have just looked at this first one and say, well, it's going to be the normal graph down 1. So I'm going to just start down here at down 1 below the origin. And I'm going to go left 1, up 1 squared, right 1 up, left 2 up 2 squared is 4. From here, 1, 2, 3, 4. 1, 2, 3, 4. Same shape. So, but we could use the zeros to kind of help us graph parabolas. Okay, this last one, we're not going to graph it. We're just going to find the zeros. So really, this is pretty much like a problem from a previous section. So we're going to put this to 0. And remember, when you factor, you always look for the GCF first. Last time the GCF was 1, so we didn't bother writing anything. But here, we could take a 4 out of everything. We could divide a 4 out, and then it goes out in front. Factoring is the opposite of multiplying, or unmultiplying, which is division. And then here, we say, all right, x times x. This is one of those special patterns. Something squared minus something squared. So we're going to get 4x, x. One's got to be a plus 2, one's got to be a minus 2, so that you get a 0 in the middle. And then we set these equal to 0 on their own. You could set this to 0 too, 4 equals 0. But that doesn't make sense. Is 4 equals 0 ever? No. So there's no solution from this one. You write it. If there was an x there, you'd get an answer. This one you solve. This one we add 2 to both sides to get the x by itself. And so those are your zeros. I'm not going to graph this one, but so that's how we do it. Today's assignment for class, honoring progress. Page 426, problems 1 through 5 all. You have little blue buttons with the video showing you exactly how to do the problem from beginning to end. If you're using the Student Dynamic ebook, which would be good to check, make sure you get each of these right before you go on to the regular assignment and the quiz, because you want to make sure you're getting them right. You don't want to waste your time. So go ahead, try it yourself.